Today, I'll slow down and I'll do a few elementary exercises, these finite groups. It's something that supposedly everybody who has graduate education in physics, chemistry, mathematics, applied math knows. In practice, you only learn it when you need to learn it. And almost nobody that I know actually knows this. It's a beautiful theory which was developed by Schur and Frobenius in end of 19th century. It's the first example of where we really have theory of groups worked out. It's really worth your learning. It's fun to learn. The fundamental insight that Frobenius had is that when all is said and done, to describe a finite group, you only have to list a set of numbers in a table called character table. And he called it character because it characterizes a particular finite group. It's also an amazing theory because today we have all finite groups enumerated, listed, and it was an amazing achievement. It was only done in the 90s, completed. But kind of groups that we have to worry about in physical and chemical applications even, mostly are small, finite, and we have started with one of these groups. We have looked at translation group, discretized, and we use that to compute the first result of periodic orbit theory, which is compute the coefficients given exact equations of motion on elementary cell or fundamental domain. And now I'd like to develop the theory of finite groups. It turns out that theory, as was realized by Weil in the 20s, is actually also the theory for continuous groups. So what we learn about characters for finite groups is transfers to a more difficult set of groups, or compact Lie groups, of which you know SO2, SO3, U1, U2, Minkowski group, etc. Number of those groups you have seen. And in modern quantum field theory or modern fundamental physics, these groups get very fancy. But I'll start humbly. So first I'll work out reduction of representations of a group with two elements. So it's a group that has identity and one operation, such that that operation repeated twice gives us identity. So it's closed under group multiplication, two elements, and it has many names depending on applications. So it's called permutation group on two elements, dihedral group of order 1, cyclic group of order 2, etc., depending on various notations in various examples. And in our applications, what these groups do is they used to tile our space. So let's have a top view of our state space M. It'll be silly, but let's say it's a bounded state space. I'll draw it in a plane just because I don't know what to draw in 1 million dimensions. And let's say it looks like some kind of butterfly or something. So it's one of those biological things which have symmetry axis. And if you know what's happening on the right-hand side, and that we'll call M tilde, we call it either M tilde, you'll see why in a second. And then there is a symmetry such that every point in the state space within half of it has its sister in its reflected state space. And what M2 is, if ME is a set of points, which I'll call tilde, so any point in this half plane, M2 is a set of points minus X tilde. And this is deceptively simple because in 500 dimensions, this operation is actually a non-trivial operation that flips some and not others, etc. But here we pretend we're in a plane. So that's a top view. Let's have a side view. In side view, we are looking at it from a side, so it might have lots of dimensions, but we represent it just as a line. And half of the line will be called fundamental domain. All the other things are copies of fundamental. Now, which domain you decide to call fundamental is up to you, but basic thing is that if you know what happens on this side, you don't have to do any work on the left side because everything on the left side is obtained just by a simple group operation. For example, reversing X. And in general, we think of this as group is 1, 2, and some number of elements. The number of elements is called order of the group. It's well defined for finite groups. And in this particular case, the first element is always identity, and then there might be some other number. So this is obtained from fundamental domain by applying all points into it, and that gives me the image. So the reason I'm drawing this sideways, because now I would like to think of functions, scalar functions, defined on this domain. And I'll call it the rho here. And that's because we're looking at densities in our application, and often we use letter rho for a density, but not necessarily a good choice. So in side view, we are looking at the graph of a function over the state space, and that could be 1,000 dimensions, but what we want to focus is the function defined on a state space. Now we can divide this into two functions. So we can call this function ρ1 defined on fundamental domain, so just the points which are in the half space. And we'll call this function ρ2, and that's defined as the original function evaluated on the image of the point in the fundamental domain. So whenever we have a tiling of the space by equivalent tiles, we will trade in a single function on the full space. We'll trade it for a vector functions ρ1, ρ2, ρd, each one of them just evaluated on the fundamental domain. The dimension of this vector is the order of the group, the number of tiles. Now, because of the symmetry, I can do all my work only in fundamental domain. So I can write this function in a way that you have seen many times. I can take the function, and I can also look at the function evaluated by changing x to minus x. So this is the original function, phi of x, but we choose to evaluate it only on the fundamental domain. And here is the function rho. And if we add these two functions and divide by 1/2, so if I put 1/2 here, 1/2 here, I'll get something that at symmetry point has the same value, but in between it'll be sum of these two functions So it'll look something like that. So this is a symmetric average over two functions. Yeah, in general, we're looking at any general function defined, and the purpose of this exercise is to tell us how to write functions that do have symmetries from any given function. So written as a formula, we can call this 1 over 2 rho of x plus rho of minus x tilde. So I can write my original function on the fundamental domain as this. And here, I'll look at the same structure. So this will be the original function evaluated minus x tilde. This will be original function evaluated at tilde. And now I can take the difference of the two. And the difference will be 0. It'll go through 0. On this side, this guy wins, so it goes up. On this side, its reflected image wins, so it goes down. And you can see that this thing is antisymmetric. This is symmetric. So I can use a notation, and I can say I can always do a linear operation where I take my original function, x tilde, and I write it as the antisymmetric antisymmetric divide on the domain. And it's sufficient to do all this work just on the half of the space. I don't need to know what's happening in reflected image, because if I have this, there's just a symmetric reflection of it. This is symmetric on the reflection, this is antisymmetric. So it's sufficient to do work on fundamental domain and look at this object. Now what I'll do with this object, I will write this in a slightly fancy way, following Frobenius. And I'll say that rho of representation alpha, which could be plus or minus, is 1 over the order of the group. That's this 1/2 here. Some number which depends on the representation. So this number in the simple case will be either plus or minus 1. So it has a label of representation. And it depends on the group element. And I sum over all group elements, which are only 2 in this case. And I look at the function where these characters are written as a character table. We write here all the group elements, the only 2, 1. And the second one I call G. And all the representation, there is a plus representation minus. And this is 1, 1, 1, minus 1. So if I stick these numbers in here, I reproduce these formulas. So this is overkill because you don't need this fancy notation, but now I'll do it for 3 elements rather than 2. You'll find it more useful. And the theory of irreducible representations of finite groups will have this structure.